with audio, video, or anything like that, please throw it in the chat and Rachel can let me know and we can try to address that. Otherwise, we'll keep going. So to start out, we want to start with a land acknowledgement. The Southern California Bight is located on the unceded, sacred, and traditional lands of the Tongva, Agjashemen, and Chumash nations, the first native peoples. They are the original stewards of this land and they continue to hold this role today. Again, to briefly introduce ourselves, USC Sea Grant. We're a federal and state university partnership that integrates research, education, and outreach with a specific focus on the urban ocean of the greater Los Angeles area and solving the problems arising out of managing people and natural resources in an intensely urban and developed coastline. This AdaptLA series, for anyone who hasn't taken part before, aims to connect local jurisdictions with the best available scientific tools to develop a community of practice in the Los Angeles region for adaptation planning. And today our guest is going to be Dr. Brett Sanders of UC Irvine. His work is primarily in environmental hydrodynamics, the specialty on numerical modeling of free surface flow and transport in rivers and coastal zones. He's a professor of civil and environmental engineering.
Literally on call.
And I think you're going to really enjoy his presentation today. So without further ado, I'll hand it over to Brett and he can take us into the presentation.
Well, yeah, thank you, Dane, and good morning, everyone. Thank you for joining us today. It's really a privilege to share some of the work that we've been doing here in Southern California on flood risk and coastal erosion. And the goal today in this talk is just to kind of lay out a sort of perspective on how many of the challenges we face along the coast are connected to how we've built and managed infrastructure in inland areas, and to sort of just shape some thinking about potential synergies that we could shoot for moving forward as we think about adaptation of infrastructure, as we are in the trenches trying to battle erosion problems along the coast, or wetland restoration along the coast, or higher sea levels. I think the idea here is to maybe shape a way of thinking that might be a little bit different from or broader than how you might have thought about some of these problems in the past. So I'll kind of lay out my perspective in this talk, and then the aim here is to leave time for some discussion so we can have multiple perspectives shared and just kind of work towards a more shared understanding of opportunities and potential for the future. I'd like to acknowledge some contributors to this work. We've been working at UC Irvine with the University of Miami and the sort of climate lab led by Catherine Mock, who's an expert in climate adaptation, working both in flood and in heat. And in our lab at UC Irvine, we've been focused on flood risk and coastal erosion. Eva Martin is a graduate student at UCI who's been deeply entrenched in this project, and Joe Schubert has been working with me for a number of years on model development and application. So my take-home message for today, which I thought I could start with, is that the flood infrastructure that was designed and built a century ago is now an obstacle to the sustainability of Southern California. So I've got a sort of a series of photos here where I've got a dam building up with sediment in the foothills, an example of a flood channel connecting basically the mountain runoff to the coast, designed at a time when we were trying to quickly move water away from developed areas to the coastline. And an example on the right of a coastline that's been sort of deprived of a sediment supply and is now, dealing with that with armoring and hard riprap, which we know has enormous sort of ecological costs and also human costs, with sort of loss to beach access and then further exposure of infrastructure along the coast. So our research team has been developing these regional modeling tools to try to better explore the costs, benefits, risks, and trade-offs of flood risk or flood infrastructure adaptation. So that's kind of our goal here is to can we develop tools that will help us move forward in a smarter, more cost-effective, more multi-benefit way with our adaptation efforts. And our goal here is with this research is to inform adaptation plans and projects, across all scales of governments and try to promote synergies between projects, as I mentioned, to realize more cost-effective, equitable, and sustainable infrastructure. So, just a couple of assumptions here, which are worth acknowledging. One is that increasing reliance on natural processes and flood infrastructure will lower maintenance costs and offer a broader set of benefits compared to hard infrastructure designs. I think one example of that is going from a completely hardened flood infrastructure to something more like what you see on the left-hand side here, which is a mix of hard and soft elements to try to provide a broader set of benefits. So not just flood conveyance, but a channel that offers sediment delivery to the coast, that offers, space for recreation, some shade from trees. Those are examples of the multi-benefits. On the right-hand side is a photo that I was privileged to see this past spring when I visited Naval Base Ventura County, an example of some of the incredible, dune ecosystems that are fronting the base there and are also threatened by loss of sediment supply. Um, so on the one hand, I think we want to lean heavily on natural processes. But on the other hand, hard infrastructure elements are necessary in many ways for certain elements of system reliability, predictability, working within tight space constraints to simultaneously meet other public needs, such as, transportation in particular. So we're kind of basically moving forward here with the understanding is, can we shift more on natural processes at the same time, continue to rely to a degree on hard infrastructure? And I think the future is some combination of these types of interventions. So in this talk, what I want to kind of walk through is part one. So how we got here, how do we end up with a Southern California environment where we've literally destroyed many of our riparian ecosystems? Part two is just an introduction to this tool that we work with to map flooding in fine detail and to explore the benefits and costs of adaptation. So part three is an update on some of the adaptation research we're doing right now with a funded project in Los Angeles County. And part four is to invite discussion, along this theme. So starting off with part one, how we got here. This is a graphic that was taken from a newspaper recounting the New Year's Eve flood from the New Year's Eve of 1933. It was published later in 1934. This flood the series of floods happened in the 20s and 30s, which were very damaging and were undermining the ability of Southern California to grow and for people to feel safe. This flood in particular, I think, like was significant in showing what really was viewed as the right solution to manage this problem. And I think it's particularly timely too, because what you see in the mountains is a mountain that's been burned by wildfire. And so they had a cycle of wildfire, then they had some intense rainfall hitting mountains covered in wildfire, then mud and debris, flowed down out of these mountains, and the floods killed a lot of people. If you're enjoy a bit of history, you can go on YouTube and look up Woody Guthrie New Year's Flood, Library of Congress, and you can listen to a really amazing sort of description from Woody Guthrie of that flood. And he describes really a fascinating dynamic of, at that time, Okies, from the Midwest and this had come out to California looking for work, couldn't afford to get a house, so they lived along the creeks and in the ravines, and they fished in the streams, get a little bit of food. They worked on the farm fields. And so with all these basically homeless encampments all along the stream beds, this flood came and washed many of those people away and killed a lot of people. That was just, and obviously there was also damage to a lot of developed properties as well. And so it was after that event that in subsequent events like this that were really damaging and brought flooding to much of Southern California, that a strategy emerged for managing these flood risks. And the strategy involved really two components. One was um, debris basins and dams that could hold the sediment that came out of the mountains up against the mountains. So it's a the first strategy was to try to keep all this mud and debris from flowing down into the developed areas where people were present. And the second strategy was to have these, streamlined channels that could take the flood water and quickly move it downstream to protect people. And the channels, like this is the Los Angeles River, and there's a photographer by the name of Kevin Brake that posts lots of cool photos of the LA River on Facebook if you're interested. But these channels were designed for supercritical flow. So that means that the flows were designed at really high fluid number. The velocities are literally like 50 miles an hour running down these streams. And so super fast flowing water. And that also contributed to them needing a relatively small footprint. So with this channel design, we were able to meet our needs for flood conveyance with a relatively small footprint, which was also viewed positively from a land development perspective because there was more properties available for industrial, commercial, and residential uses. So so that was kind of like I think like the 30s and 20s and 30s and then early 40s that we had a strategy of debris basins, dams, hard infrastructure. That was going to be the strategy that would be used in much of California to protect the urban areas along the coast from flooding and to support economic development. Um, and you might ask, well, why did it spread so much across the state? And so much of the state has dealt with this infrastructure. And a real gem of a paper was shared with me by Matt Kondoff many years ago. This paper by William Kyer called "Diverse Interests in Riparian Systems and Their Potential for Coalition." Um, but I thought I'd read this for everyone's benefit. And the first paragraph here on top is that it reads, "The state's flood control policies were enacted in 1945. The California legislature had a problem in 1945. It had to decide what to do with an enormous budget surplus which had accumulated during the war. It decided to spend the money on a scatter of capital improvement projects, mostly local government programs. Flood control was one of the lucky winners." Okay, so imagine World War II has ended. California has had tons of factories that built goods for the war. Tons of tax money was in state coffers, and so you got all this money sitting around. What they write is at this point it should be spelled out what has always seemed obvious, but may not be in fact be. That is, during the years in which the 1945 policy was applied, there was virtually no way that local officials could say no to a local flood control project. It did not cost them a cent, and it made developers and other boosters happy. The planning was done and is still done by the federal agencies. The California legislature authorizes each project for state assistance. The local agency proceeds to buy the necessary lands, relocate railroads and pipelines, raise street and highway bridges, periodically billing the DWR for reimbursement. When the project is completed, local government planners and developers attack what was once a riparian system and produce residential, commercial, and industrial properties, which in turn produce the tax revenues necessary to maintain and operate the flood control project. So many of you know today, you go to get federal money for a project, you have to come up with your cost share. So basically, the cost share was covered by the state of California in the 1940s. And that made it possible at local level to get whatever infrastructure you wanted paid really quickly and built really, really quickly. And so statewide, we have this rapid expansion of flood infrastructure. And this is a diagram showing with these little white dots are all the debris basins just around Los Angeles County. And the blue dots are dams across Los Angeles County. So you can see the way in which infrastructure, rapidly proliferated. Um, and the impacts for the coast are substantial. This study by Sherman and co-authors documented that around 4 million cubic meters of sediment are accumulating every year behind dams and debris basins across Southern California. So you can also do a little math on that. For those of you managing erosion along the coast, 4 million cubic meters a year at a cost of getting the sand there, say 10 to 100, dollars per cubic meter, you're looking at like a cost here that could easily be like $400 million per year facing the region. Okay. And now we have this sort of suite of environmental challenges that we're facing. They're all connected. So we've got coastlines, they're losing their beaches, infrastructure that's exposed. We've got dams that are filling up with sediment, which means they don't offer the flood protection they once offered, and they're going to be very expensive to try to clean out and restore. We've got a number of, miles and miles and miles of flood infrastructure connecting the mountains to the coast, which are not offering much in the way of ecosystem services. We don't have it's rivers without vegetation and soil, no shade, poor water quality, no habitat for ecosystems, no green space for human well-being. And this is some paper results from Karen Thorne and colleagues that was published in Science a few years ago, just pointing out that wetlands along much of the West Coast are facing sea level rise and likely inundation. And I pulled out the results from 3 Southern California wetlands that are appeared in that paper, including Newport, Sweetwater, and Tijuana. And they're looking at marsh habitat in this paper, and they're documenting the likely shift in habitats from mix of like high marsh, mid marsh, and low marsh, and with rising sea levels predicting sort of a considerable loss of high marsh. So we're not seeing like any likely high marsh in sort of as of 2100, and much more mudflat and low marsh type habitat. So this is a concern now, managing coastal wetlands. The sediment supply is unlikely to keep up with the sort of inundation rates or the sea level rise rates along the coast. And so sediment supply really figures prominently in that, trying to manage those trade-offs. In much of Southern California, there's not land available for these marshes to migrate inland. So what we're looking for are strategies to help the marshes move vertically upwards to try to maintain a similar mix of habitats. And then we did a study a couple years ago now, which documented that even with this infrastructure in place, this flood infrastructure, because of the increasing urbanization across the region, there's been higher and higher flood peaks in this main stem drainage system over time. And some analysis that we did suggests that around 425,000 people and $56 billion in property, could be exposed to the sort of flooding at the 1% annual chance level, which is not presently mapped by existing FEMA maps, and those haven't been able to keep up with changes in land use and changes in climate and so on. In our work, we also pointed out that in the presence of this flood risk, there's a disproportionate exposure for Black, Hispanic, and disadvantaged populations. So that paper that I just showed you illustrated in an application of this tool called Primo that we developed at UCI, which allows us to simulate flooding down to the household level, but doing so at the regional scale. So we solve equations, the same equations that are used by HEC-RAS. If anyone's familiar with HEC-RAS type modeling, or two-dimensional equations. The model's designed for fine resolution simulation of large urban regions. We account for infrastructure like levees, culverts, storm drains, and pumps. We can also now account for infiltration and seepage, which are some new functions we've been working on the last couple of years. And the model runs fast. So if you're interested in learning more about the model, this is a paper that was published this past year. It appeared in Earth's Future. It probably has the most up-to-date summary of model functions and also citations to other papers that describe the model as well. But that's the Primo model. And with support from NOAA, we've been testing this model out as a tool for building understanding about flood risks and collecting ideas about how to manage it. And then in this project that I'll share with you shortly, we are trying to sort of map out how the flood risk might change under several different adaptation scenarios. But the gist of this model is by having a fast response model that can simulate flooding under many different potential interventions and many different future climates, we can sort of iterate a decision-making process to try to bring more factors into consideration into this adaptation process and help us work towards plans and responses that are going to be effective and equitable and affordable. So part three here is moving along, exploring adaptation options. This work has like I mentioned, been supported by NOAA and facilitated by the Los Angeles Area Collaborative for Climate Action, a LARC Center, which is based at UCLA. And we are, through that iterative process, coming up with a set of scenarios to model to try to map out how the benefits of our infrastructure might be different under different adaptation options. So we're kind of looking right now at sort of four different types of interventions. One is the tried and true raising levees, hardening channels. Those interventions are directed at more channel capacity, main stem channel capacity. A second option would be channel widening and restoration. So imagine the narrow flood channels we have being widened, and instead of having a hard surface, having soft elements and vegetated elements to restore some natural processes and functions. A third option we're exploring is sort of highly distributed stormwater capture. So the idea is to promote more infiltration and seepage of rainwater into the ground, to try to reduce the stress on the main stem infrastructure, and also at the same time bring more benefits of green spaces and soft surfaces into the urban landscape. And the fourth option we're looking at is sort of dam operations and pumping. So, how much flexibility is there in the main stem flood infrastructure system to alter the way alter the operation of dams, and so we'll explore that to a degree. So those are kind of the scenarios that we've been developing over the past year, and we have some preliminary results on that front. In the next year, we're going to be moving on to an evaluation framework that helps us map out for each of these options the relative economic, social, and environmental benefits of these different adaptation options. And the aim here is to kind of come up with a set of scenarios that allow us to more fully think about the costs, the risks, the benefits of these different scenarios, inform discussions about trade-offs, and shape future plans and investments. So I'm going to walk you through one specific result just to give you a flavor for how this modeling system one example of types of metrics we can get out of the modeling system. And in this case, what I've done is modeled the 1% annual chance flood risk based on existing flood infrastructure today. And that's shown with this sort of medium colored blue here. And we can see the spatial distribution of the fluvial flood risk. We can see that we can estimate the damages that would likely occur to properties, as an example. We can estimate the number of people and the density of people that would be exposed to that hazards. And so with this scenario, we have some estimate of what would be the likely, damages to properties. And also we can estimate how many people would be impacted. And that's one metric of many that could be considered in an adaptation assessment. Okay. Now, if we take those numbers and we plot them in a bar chart, we have flood damage on top here, and we have flood exposure below. So this is people exposed, and this is property exposed. And we can see that we can break that number up, that medium blue number, which corresponds to this, can be thought of as a bar chart. And you can break that up by social groups. So we use census data and looked at population that's Black, population that's Hispanic by ethnicity, population that's Asian and white. And so you can sort of look at the distributions of how many people from different social groups would be impacted in terms of the property and also in terms of it's basically, and also in terms of the population exposed. Um, then you can also do what's called an inequality analysis, which is to say, is um, is that number of people exposed proportional to the population, or is it somehow disproportionate to the population? So that reveals this Gini index, which is shown here. And if the Gini index is positive, that means that that social group is disproportionately overexposed to that risk. And if it's a negative number, then that means that that social group is disproportionately underexposed to that risk. And so one of the takeaways from our first study of flood risk in Los Angeles was that Black populations were disproportionately exposed. And that's shown here by this Gini index of around, say, zero point 0.3 here, and down here for the population was almost as high as 0.5. So it's a pretty strong inequality. Conversely, if you looked at white populations were disproportionately underexposed to this fluvial flood risk. So that becomes one of numerous metrics that you can think about in terms of risks and inequities, and trying to work towards an adaptation strategy that's more effective and more equitable. So now let's consider an intervention. Let's consider raising levees. So this orange color here corresponds to the flood hazard distribution, assuming we raise levees by a meter across all of the main stem flood system in the region. And so we still have some overtopping predicted by the model, but it's reduced a lot. And if you notice in the bar chart here, the exposed property would be reduced significantly. The exposed number of people would be reduced significantly. And so on the one hand, you think, well, the higher levees looks like a really effective solution. We can reduce exposure, we can reduce exposure properties and people. But one thing that you'll note here is when you compute the inequality metric, it really didn't change much compared to the baseline scenario. So we didn't necessarily erase those social inequalities. So then you can have a debate. You can have a sort of a fair debate around whether a project is an effective project based on which community groups are beneficial, which geographic groups benefit from the project, and so on. And I'll point out that we also explored scenarios with a lower flood peak. And if we could somehow increase the amount of stormwater capture and reduce the amount of flow into this main stem system, we could potentially lower flood peaks. And that seems to be a recipe for not only reducing exposure, but also reducing inequalities in exposure. So this is some preliminary results just about how this modeling system can generate different types of metrics that can then feed into this sort of conversation about equity and adaptation. Another direction we're taking is in channel widening. So this is a map we've put together of all of the flood channels, developed flood channels across Los Angeles County. And what we're doing in this scenario is imagining that we take the existing channel footprint and we triple it. So we add a channel on either side. And the idea there is to sort of say, how would this change the flood risk distribution? What would be the cost of land acquisition and, say, bridge replacement? If we did this kind of widening, the idea is to kind of triple it. If you triple the flood channel width, that gives you the ability to increase the resistance of the channel by a factor of 3 as well. And so with that increased resistance, it's referencing the potential for more natural channel with a broader set of benefits. So it's just a way to sort of put that idea into a scenario. So that scenario is coming along. I don't have results in terms of how much it changes flood risk, but it does alter flood risk. There is a big cost. And then another scenario we're developing is to explore a stormwater capture scenario. We've acquired 1 meter resolution imperviousness data, and intersected that with many different groundwater basins in the region. We've also acquired soil hydraulic conductivity data and infiltration data so that we can estimate if, depending on how much reduced imperviousness we invest in, how that could potentially change the amount of stormwater capture, which would be a benefit to the region, and also potentially reduce flood peaks. I think previous work has shown that the more severe the flooding, the less impact imperviousness can make, because eventually on these wettest, most severe storms, the ground is almost fully saturated anyway. So having more imperviousness doesn't necessarily mean you're going to get a reduced flood peak. But there's events of many different return periods for which this could, document benefits. And so our plan again is to just explore these trade-offs and try to map out the distribution of benefits. Another knob that potentially could be turned is how we operate the main stem dams. And this main stem system, like Hanson Dam and Sepulveda Dam and Santa Fe and Whittier Narrows, um, most of those are operated by the Army Corps of Engineers, and the LA County operates much of the higher elevation reservoirs that up in the mountains. But most of these reservoirs, flood control reservoirs in the lower basin, are operated in a way that you prioritize flood control. So they try to release as much water as the downstream channels can handle and not create a flood risk. But what that means is there is some flexibility for smaller events to alter the way they operate to try to change the environmental benefits or the social benefits. So there could be some flexibility within the dam operation space to think about different types of benefits besides flood safety. For example, environmental benefits. One of the exciting ones I think to be thinking about is sluicing of sediment from dams down to the coast. So with some changes to dam operation, there could be some feasibility of sluicing sediment from these dams down towards the coast. And we're working on a framework to take these different model scenarios, the data we have, the models that we run, and try to come up with a set of metrics that will inform our thinking about the economic evaluation, the social evaluation, and the environmental evaluation. We're imagining producing a lot of metrics and then feeding this through a distributed justice analysis. And that will be led by Catherine Mock, and I'll have more to say about that in probably a year or so. And the last couple slides here, all this is not meant to prescribe a particular solution for Southern California. What we're trying to do is build some knowledge about some of the trade-offs between some of the investments we make in inland areas, some of the challenges we face along the coast, and have the kind of science and knowledge and tools that are available to feed into regional planning. I think this emerald necklace plan that was envisioned, was it 100 years ago by Olmsted? It's been resurfaced by this group, Amigos de los Rios, as sort of a guiding principle for regional adaptation. I think these are the kinds of things we could support with our tools and knowledge, this kind of adaptation planning. I also want to point out that I don't want to give the false impression that everybody needs more sediment along the coast. We have embayments that fill up with sediment, like Upper Newport Bay. It's been a problem, and LA Harbor, Long Beach Harbor. They would prefer not to have a bunch more sediment coming down the river and filling up their harbor, which they would then have to dredge and move somewhere else. So there's also this challenge of trying to get sediment where you want it along the coast. For example, erosion hotspots in Newport. Seal Beach wetlands is an area where they've brought in sediment to try to raise the elevation of the marsh. South Orange County has been hit really hard with coastal erosion. They would love more sediment down here. And I also wanted to take a moment to pitch a tool called the SETIMATCH tool, which was developed at the San Francisco Estuary Institute. But it's a tool that allows users or those who need sediment to find those who have sediment. And Lisa Haney from the Orange County Water District has been trying to kind of elevate this tool as a resource for Southern California. So if you're interested in learning more about this SETIMATCH tool and finding a partner to either find sediment or to get rid of sediment, this is a great initiative coming along. And I wanted to close with this final thought, which is that we know a lot about the way our freeway infrastructure, divided communities, impacts the environment around communities with air pollution, I don't think we know as much about the way that the flood channels divided communities, the way the flood channel infrastructure impacts um, heat waves and creates desert islands and things like that. So the idea here is to imagine a future where flood channels offer a broader set of benefits to Southern California communities, not just flood control potential, but things like trees, shade, access to nature, better water quality, stormwater infiltration, and sediment delivery to the coast. So that's your deep thought for the day. So thank you very much for your attention. I'd be delighted to be a part of the discussion.
Awesome. Thank you, Brett. So for discussion, if people would like to put questions in the chat, I see that we already have one from Sabrina. Or if you would like to raise a hand, we can call on you and you can unmute yourself if you'd like to give your comment or question in person. So I guess to start out, Sabrina's question was, if you sluice sediments to the coast, do you need to separate by grain size first? And where would the fines go? And mentioned the Matilla Dam removal planning and found that was a difficulty.
Yeah, thank you. Thank you for that question, Sabrina. And we don't know yet, how effective sediment sluicing could be. It's complicated, as Sabrina points out. There's a distribution of grain sizes. Um, I think there is also the Southern California region has pretty steep slopes, has pretty fast velocities, but we don't know if we release sediment, if that material is just going to mainly accumulate and settle out in the channels, let's say a mile downstream of the dam. If all we do is get sediment out of a reservoir or from behind a dam and we just move it a mile downstream and we create a flood risk for an inland community, that's not going to be, I think the kind of solution we would want to have. But let's flip it on the other hand. Say we find a set of events for which we can expect, a good fraction of the sediment released from the dam to make it all the way to the coast. And there's going to be some sediment left over settling out in the channels. We might decide, what, that's a trade-off we can handle, and that's going to bring a better set of benefits. But this is an area where I think more research is a priority to try to understand across Southern California and across much of the West Coast. Are there can we devise? Is it feasible to sluice sediment to the coast? And another question is, could you re-profile the cross section of the channel in such a way that it was more effective? And so I think the knobs here are, the time scale of the hydrology, the sediment size distribution, the slopes of the channels, the length sediment needs to move, and you've also got the cross section of the channel, and those are things you could potentially, study as ways to think about sluicing to the coast.
Yeah, I would recommend that people kind of look at some of the materials we produced around Matilaha Dam, and I could put people in touch with Ventura County Watershed Protection District, or you can certainly contact them yourselves. But just to raise another point, a lot of some of these sediments are not clean. They can be contaminated from upstream uses. They can be contaminated from fires. So yeah, there's definitely complicated sort of cost benefit analysis and a lot of analysis of the sediment itself needs to be done before really determining whether the benefits that are sort of the theoretical benefits could actually be realized.
And to share an optimistic tone, Orange County just the last couple of years has made it a point to scrape up much of this clean sediment from flood channels and make it available along the coast to nourish beaches. So I think that there are examples of clean sediments today that are being taken out of flood channels as part of regular maintenance processes, delivered to the coast. And in doing so, you're sort of restoring a natural process that's been impaired by and modified by the dam and flood infrastructure we have today. So there is a place here to I think make a difference, and but it's not going to be easy, as Sabrina points out. There's anybody who moves sediment knows there's a million permits and testing and everything else that can make it a tough slog.
Thank you. I think the next question or next hand I saw, Madeline Glickfeld, if you want to unmute yourself.
Hi, thank you for a really excellent presentation. I'm just writing you a note, which is that I'm looking at some of the solutions that you have, and it would be great to see the work you've done sort of combined with other kinds of disciplines. For instance, not every place can have, I'm looking at the distributed infrastructure, which is a example that I have a lot of familiarity with. In LA County, only 20% of the land has the possibility of has permeable enough soil to get water down to groundwater. So it's not solution everywhere. And I have found that with looking at projects for distributed infrastructure, if you're doing it with a public agency money, you're going to spend as much money doing many small ones, or more money doing very many small ones than you do with large. So the way that they cost things out and the kinds of requirements they have really increases the cost. You can't do things simply. And there are public health issues involved as well. How well are you going to be able to treat? How well you will be able to monitor whether the water is clean that you're sending down? What kind of impact does it have on the plume? So there's a lot of interdisciplinary questions here, but thank you for showing us the model, because it at least allows you to ask some of those questions.
Well, thank you, Madeline, for the comment. If I got that right, the name right, and yeah, acknowledge that like we can only do so much, with our team and our sort of our tool, but we are trying to kind of offer some sense for the trade-offs that we made. I don't think we've really done much to understand what are the trade-offs between widening channels, raised, taller levees, trying to capture more infrastructure. We are trying to, we collect information about infiltration rates. We know that you're only going to really get water into the groundwater basins in areas that have unconfined aquifers. But even where there's confined aquifers, there's still some infiltration, some seepage that takes place into the subsurface and shallow groundwater. So we're just trying to sort of have a tool that allows us to learn more about the response of rainfall to runoff and the stress it puts on the main stem system. And we'll see what we can figure out. Yeah, I completely agree that going to the next step of trying to figure out exactly what things cost is extremely difficult. But there may be some examples like the one you point out that we can lean on to get a better sense of what those costs are.
But there's a lot of work going on in this area now, and so I would hope that somebody would help to bring your work together with the work that's going on.
Thank you. The next question I saw in the chat is from Rosie Daggett, asking, how do you envision prioritizing or weighing the model indicators that you're analyzing?
Yeah, great question. So in my view, like the metrics tend to be something that stimulates a conversation, that builds understanding, and they're kind of looked at in a qualitative sense and in a relative sense. I don't have any plans for some Uber indicator that somehow describes what's optimal. But I think that the metrics do help to shape people's thinking about what we're trying to get out of a project, and maybe strengths and weaknesses of a project. So I'll probably have a more informed response about that question in a year or so after we've kind of sunk into that part of the project more. So for now, I think I'll just end with that brief comment.
Thank you. Next one is from Natasha Kumar, asking, How have Native peoples been incorporated into this conversation? Do they have any oral history or knowledge about historical flood influences on the LA basin and the natural pre-Spanish, pre-American colonial system and how that changed the land?
Oh, thank you for the question. We've been working through the Los Angeles Regional Collaborative for Climate Action and Sustainability as a way to invite participants to come and be a part of this process. Um, we could do more to engage with more Native groups. So I can't, comment much more about that, but be we'd welcome the opportunities to connect more about on that front.
And that was all the questions I see in the chat. One did ask if you would be willing to share the slides from the presentation, which we can send out in our
Yeah,
follow-up
I'd be
email.
happy to share the slides. Sure.
Awesome. Any other questions if people want to raise hands or submit in the chat?
And I will also comment that the process of evaluation in our framework will be an open process with meetings facilitated by LARG, and those will happen over the next year or so. So we would be delighted to have participation by those interested, including Native groups, and I can if you want to contact me directly or contact Aaron Coots at LARC, that's a mechanism to be involved in those meetings.
All right, I'm not seeing any other hands raised.
I'm going to drop
Phyllis. See
Aaron's
Phyllis.
email into the chat, and like I said, we've had open meetings to try to encourage governments and non-governmental organizations to share their thoughts on data we can consider, methods to consider different factors in this project.
Phyllis, I think I saw a hand raised there if you wanted to jump in.
Yeah, I just want to thank Brett for the presentation. It was really interesting. Thanks to my team, to California Shortage Preservation Association, our co-host for this. And we look forward to keeping up with this and maybe doing this again in a year, as you're suggesting. So thank you, everybody, for coming, and thanks again, Brett.
Yeah, thank you, everyone.
Awesome. If people don't mind hanging out just for a minute longer, we have a 2-question follow-up survey that really helps us guide our programming. So let me switch to my presentation. I know we're losing some people probably to lunch, but if anyone doesn't mind staying for a minute, that would be great. Sabrina, I see your hand raised. Did you have another question?
Yeah, just quickly, I may be joining a team to work on some projects with the Army Corps in Maryland, and I think that this model could be really useful for that. Is there any reason it can't? I mean, obviously I'd be contacting you directly, but this should be applicable to other regions, right?
Absolutely, yeah. We've have
Great.
models set up in Miami right now, and Southern California, and Georgia. So we have a few different sites where, through collaborators, we're working on different aspects of the flood adaptation challenge.
All right, so for
Great,
those
thank you.
that are still here, maybe 1 second just to switch.
And thank you, everyone, for your attention, for being a part of this. And it's obviously a privilege to be able to come here and share what we've done. And welcome any feedback if you want to send a note or anything like that by email. Thank you very much.
Yeah, and so just a very quick follow-up survey, if you don't mind, there's a link in there There's also a QR code you can scan with your phone, or Rachel dropped the link in the chat to a very quick Menti survey that just gives us some feedback on what we're doing with these AdaptLA meetings and what people hope to see in the future. So I'll give people a quick second to join that. And once you join, there should be a little thumbs up button in the bottom. So if you don't mind hitting that, that will give us an idea. I will start that right now. All right, so if everyone is in there, looks like we've got 11, 12 people. The first question is just giving us a little bit of feedback on how useful this was. So on a scale of 1 to 5, go ahead and hit those, and then you can hit submit. Awesome. I think that's most of the people that are still here. Thank you all. And our next one is more open-ended. So in just 1, 2, 3 words, are there any topics that you haven't heard covered in the AdaptLA webinars or in other areas that you would like to see us talk more about? This was us branching out a little more upstream than pure coastal erosion patterns and trying to bring more of the watershed considerations and the flood infrastructure into the conversation. So if there's things like that or things that you think we've missed and you would like to see, please put them in right now. Right, these are great. Thank you all for these. Give it another minute or so. And when you're done, if you don't mind hitting that thumbs up, that lets us know that you don't have any more to add. All right, that looks like it. Thank you. It looks like coordination and funding are the biggest, which makes a lot of sense. So uh, we're going to capture that for our records, and we will try to incorporate this feedback into our plans for the future. So thank you again. And thank you for taking part in that. And I'm going to switch back over here for our last slide, which has contact information for myself and Rachel. Again, we're the Coastal Resilience team here. So feel free to reach out with any questions or comments to us. Brett's email is there as well. And shout out to our partner in this presentation and our next upcoming presentation, which is the California Shore and Beach Preservation Association, which is the California state branch of the ASBPA. they're helping produce this one and our next one, which will be on Wednesday, November 13th, which is going to be one of the USC researchers who was, I believe, on this webinar as well, and looking at projected shoreline erosion rates in Southern California and trying to quantify some of those sediment and nourishment needs for future protection. So tying right into this conversation about sediment sourcing and sediment coming down those river systems, but more from the coastal perspective. So please join us in a couple weeks for that one. And if you're interested in these AdaptLA webinars and series and information, join our AdaptLA newsletter, which the link is there on the bottom, or if you simply Google USC AdaptLA, that should be the first thing to come up with a link on the bottom to join the newsletter. We will be sending a follow-up email with links to some of this material from Brett, and we'll get his slides shared out as well so that people have the links that he had incorporated into those. Thank you all again, and looks like we're right on time. So have a great afternoon, and hopefully this was a good start to your Monday.